Welcome to Science Spectrum with Don. This is the 8th part of the 3rd lecture in measurements of length. So far, we have learned just a few things about the Vernier caliper. And we saw you could measure both the inner and outer diameters of curved or round objects. And of course, you could measure the depths of hollows in objects. All right, so let's proceed. Let's proceed. Now, from the previous class, I mentioned to you that 9 divisions, which is the same as 9 millimeter on the main scale, right? That we could fit 10 marks or divisions to 9 main scale divisions. So what it simply means is 10 Vernier scale divisions, right? When we express it in terms of the main scale now, it is 1 less than 10, that's 9 main scale divisions, right? So if I could divide through by 10, we could see that 1 Vernier scale division is, this is in millimeter now, right? Because the smallest mark here is millimeter, so this is 0.9 millimeter. So 1 Vernier scale division is just 0.9 millimeter. Now, I want to talk about what we call the least counts. That's what is simply least count. It is simply this. This is the shortest interval between the main and the Vernier scale. I could really, let's see, I think it's just something like this, right? Something like this, okay? This is what we call the least counts. This is the least counts, okay? That's shortest interval. The shortest interval, right, between the main scale and the Vernier scale. All right, so the least count of the Vernier scale, the least count, we also call that accuracy, or we could use the word accuracy. At times they use the word Vernier constant. It means the same thing, right? So this count is LC, this is LC, right? This is VC, as you like it. So they all mean the same thing, right? That's shortest distance, right? The Vernier scale could slide across the main scale, like I just showed you earlier. All right, now the least count is simply 1 main scale division minus 1 Vernier scale division. Now, 1 main scale division, we could see from here that if 10 marks, 10 equal divisions here is 1 centimeter, right? So it means 10 of those marks is 10 millimeter. So it means 1 would be 1 millimeter. Is that correct? So 1 main scale division is just 1 millimeter. So this is 1 millimeter minus, then 1 Vernier scale division is 0.9 millimeter, right? So when we subtract, we get 0.1 millimeter. This is the least count, right? So that's the shortest distance, right, with which the Vernier will slide across the main scale. Now I may need to rub this off. You need to beam this for a while. You need to rub this off. All right. The drawing is not a perfect one, but just to make you see. This I don't have the instrument with me. All right. Now, since we know, we've established the fact that 10 Vernier scale division, right, would give us 1 less than, right, the Vernier scale division on the main scale. So this would mean that n number of Vernier scale divisions would be n minus 1 main scale division. So if I have a 10 here, this would be 9, just like we've seen here. All right. Now, so if I divide through by n stands for, okay, number of divisions. So if I divide through by n, can you see that 1 Vernier scale division would be n minus 1 over n of the main scale division, right? All right. Now, least counts, aside from, okay, the fact that it is 1 main scale division minus 1 Vernier scale division, and we saw it as 0.1 millimeter, right? Now, another way we could do this, that's for the least counts, and anyone you prefer, be my guest, right? So least count is 1 main scale division. So it is 1 main scale division, this is least count now, or Vernier constant or accuracy, minus, so 1 Vernier scale division now is this, right? So it is n minus 1 of the main scale division divided by n. So let me quickly multiply this. I have 1 main scale division. This is n times, this is n main scale division divided by n. So I'll get a 1 main scale division here. Minus times plus, this is a minus. This is a minus. So this is a minus. So I have 1 times, this is just main scale division divided by n. So this is a 1, right? Okay, so if I open up the bracket now, get 1 main scale division, this will divide out. So I'm left with minus 1 main scale division. Minus times minus gives me a plus. So I'm left with 1 main scale division over n. So can you see this term cancels out? So least counts could be either 1 main scale division minus 1 Vernier scale division, or it is 1 main scale division divided by the number of Vernier scale divisions. Right? Alright. So we could use this for least counts, or we could use this for the least count. Alright, so to check this out now, 1 main scale division is 1 millimeter, right? So this is 1 millimeter. And the number of divisions on the Vernier scale, right? We saw it was 10 divisions. So when you divide out, definitely you will get 0.1 millimeter, which is exactly the same as what we had earlier on. Now, how do we make measurements with the Vernier scale, right? We know until the jaws, right, it's held firmly to the object. It could be, you want to measure its inner or outer diameters, right? Or even the depth of its hollow. But how do we really read those values? So let's get to that shortly. Alright, you need to build this for a while, and I could wipe it off. Alright. So now I need to say 1 or 2 things. 0.1 millimeter in the least count on the Vernier caliper, right? So it also means that I could also express the least count on the Vernier caliper in centimeter. So all I'll need to do is to convert 0.1 millimeter to centimeter. So 0.1 millimeter, I do know that 10 millimeter is equivalent to 1 centimeter, right? So you could see that millimeter will cancel the millimeter, and I'm left with centimeter now. So 0.1 times 1 will give me 0.1, and I'm dividing by 10, so this will give me 0.01 in centimeter. So 0.1 millimeter is the same as 0.01 centimeter. So this was what I talked about earlier on when I talked about the accuracy of the Vernier caliper, that it could measure to 1/10 of a millimeter or to 1/100 of a centimeter. Alright, now let's see how we use you need to build this for a while also. So let's see how we use the Vernier scale. Can I rub off? Okay. So let's see how we use the Vernier scale. Now, the Vernier scale, let's see shortly, could have some errors, right? We could have no error. We could have what we call the negative 0 error. We could have what we call the positive 0 error. But let's see. Now, if I have a Vernier scale like so, I mean, this is the main scale. So this is the main scale up, and this is the Vernier scale. Now, this is the main scale, and this is the Vernier scale. And let's say this is in millimeter, right? So the main scale is in millimeter. Now, this is the Vernier scale, right? Now, if the jaws A and B, like I drew earlier on, of the Vernier scale, right? It's joined together. The same goes with jaws C and D that could measure the inner diameters of objects. Once they are joined together, and you could figure out that 0 mark on the main scale aligns with 0 mark on the Vernier scale, right? It means in that kind of scale, there is no 0 error. There is no 0 error in this, right? But we could also have what we call the negative 0 error and the positive 0 error. What this simply means is this. The Vernier scale, okay, could shift to the left of the 0 of the main scale. We call that the negative 0 error. And the Vernier scale could shift to the right of the 0 of the main scale division. That is if both jaws A and B, jaws C and D, right, we're touching each other from, of course, okay, what it means is there is no objects in between, so it's properly screwed. They touch each other, still the zeros do not align. Alright, so let's see. So let's say I have this is the main scale, this is the 0 on the main scale. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Of course, it could go beyond this, definitely. But if I have a case where the 0 now on the vernier, this is the main scale. So if the 0 on the vernier is to the left, can you see? This is the vernier scale now. So its 0 is to the left of the 0 on the main scale, and both jaws are touching each other. In other words, there is no object in between or any space in between the jaws. This we'll call the negative 0 error. This is called the negative 0 error, or just say negative error, so to speak. Alright, so let's assume that, okay, let me stick in some markings now. This is, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And let's see. Okay, this is 10. Yeah, this is 10. So can you see that the third mark on the vernier scale, this mark here, this is 0, 1, 2, 3. So the third mark on the vernier scale aligns or coincides with the main scale division, right? So we call these points, the point of coincidence. This point is called the point of coincidence. Point of coincidence. That's the point where the vernier scale, that's the vernier division, aligns with the main scale division. Alright, so how do we really make room for the negative 0 error now? We could calculate this with a general formula. It is simply this is the number of main scale division, right, before the 0 mark on the vernier scale, right? And of course, we could see this, that, okay, we could just ignore this part, plus the number of the vernier scale division now that merges with the main scale division multiplied by the least count. And of course, we know what the least count would be, both in millimeter and in centimeter. In millimeter, this would be 0.1, and this would be 0.01 in centimeter. Alright, so now the mark that's of the vernier that coincides with the main scale division is the third mark. So of course I know I could just stick in the 0 here. So this is definitely 3 times the least count. Let's say this is this scale, if it's in millimeter, so this would be 3 times the least count, which is 0.1 millimeter. And of course I know that the negative 0 error here is minus 0.3 millimeter. So what this simply means is, if I now measure the diameter of an object, right, and I could read off its actual value from this formula, we'll get to that shortly. It simply means I have to add 0.3 millimeter, not the minus now. I'll tell us how, okay, it will become a plus. So I have to add this negative 0 error to it to make up for this gap, right? So that will tell me the actual value of the objects, okay? All right, now we could have the positive 0 error. The positive 0 error. Positive 0 error. It is simply, this is the main scale, 0 on the main scale. It is when the 0 on the vernier scale is, okay, after the 0 on the main scale. That's positive 0 error. So this is, let me stick in some marking. This is, okay, let me just say this is 1, 2, 3, 4, 5, 6, 7, 8, 9. And let me fit in 10 divisions here. So let's say this is the 0. So let me start here. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. Can you see 10? So there is a gap left here. So can you see now that the 8th division, right? The 8th mark on the vernier merges with the main scale division. So this, from this same formula, right? Since I know I don't really have any value of the main scale, right, before the 0 on the vernier, so I could just ignore this and I could just work with this. So it is n times the least count. N is the main scale division, that's the vernier division that merges with the main scale division, and this is 8. And of course, if this scale had been in millimeter, definitely this would be 0.1. So this would be 0.08 millimeter. Now I have to subtract this from my total reading. Now, if you're new to the channel, you may need to like, share, and subscribe for more content.